Welcome everyone to our talk on the principles of differentiable quantum programming language. This is a joint work with Xiaopeng Zhu, Shihan Hong, Shavanik Kurbati, and myself. We're from Joint Center for Quantum Information and Computer Science at the University of Maryland. The talk is about two emerging programming languages. One is the quantum programming language that operates on future quantum machines. The other is a differentiable programming language that's supposed to give us the next generation machine learning applications. The talk is about the happy marriage of both. Namely, we talk about differentiable quantum programming languages. However, this is not just a burn teaser, but also with strong practical motivations. With the establishment of a quantum supremacy, we now have a machine that we can barely match with our classical computing power. One prominent examples of applications for the near-term quantum machine is called variational quantum circuits. The training of such applications requires gradient computation that involves matrices as large as like 2 to the 53, thus infeasible for classical computing power. Thus, using quantum programs to compute the gradients of quantum programs is critical for the scalability of gradient-based quantum applications. However, to study or define or formulate differentiable quantum programming language will face conceptual challenges from the very beginning. So let's start with a very simple classical example. Let 3 to be the product of V1, V2. And if we want to compute the gradient of V3 or derivative of V3, we can apply the product rule. We got V3 dot equals V1 dot times V2 plus V1 times V2 dot. Here's some observations going to be critical for comparison between classical and quantum. So first, we actually observe all the computation, the internal state of them are those VIs, are also the way we represent them. And all those VIs, they're real numbers and thus differentiable. So there's no question about defining derivatives. We can store all of them and their derivative at the same time. There's no worry about that. And because of we can do that, we even have a fancy tool based on the chain rules. If you think about the quantum, which might be new to most of you, since they're slightly different, you still have a classical input x. But in order to run them on quantum machine, first you need to encode them as a quantum state. Then you can apply the quantum operation, which by itself are unitary operations, U1, U2. In order to read information out, you need to make a measurement. There's something we refer as quantum observables. Then you can recover the classical output. The key difference here is that in quantum computation, the actual state of the computation is a quantum state. Its classical representation is something we know, but it also could be exponential size in a matrix. If you consider like a unit operation on the quantum state, assume it takes unit time on quantum machines, classically simulating that based on the classical representation amounts to computing like U1 row, U1 dagger, which could take exponential time because it involves exponential size matrix modification. Because of this difference, it's actually pure unclear what will even make sense if we say take maybe partial row, partial theta for something. And because there's no cloning theorem for quantum states, it's hard to imagine we can store all the intermediate state rows. It's just impossible. And because we lose all those nice features in the classical, it's hard to make sense of chain rule either. So let's zoom into the actual case we care about. Think about the classical neural network, which weighted classical circuits give you a mapping from X to Y. The promise of a quantum machine learning is that it potentially gives you another mapping through X to Y, but through quantum. Replacing the classical mapping by the quantum one could have potential speed up, at least because we don't know how to efficiently simulate this quantum mapping. So it could give you something you cannot efficiently compute by classical means. The variational quantum circuits exactly models this, where we use classical parameters to parameterize those unitary operations in the quantum setting. So like the classical neural networks, in order to train over those parameters for the variational quantum circuits, we need to optimize the loss functions. The loss function L here depends on your input X, your output Y, and theta. However, for the quantum setting, the output Y had this particular formula, which comes from quantum mechanics. It involved exponential size matrix modification and take trace of those matrices. We do know if you want to take gradient of L, you can just take gradient of Y, and that will roughly enough for you to compute the gradients. Use the best way to train the loss function. Well, the cost will be exponential. We know for very simple P, there's some quantum procedure can help you to compute this Y or the gradient of this Y efficiently. However, this is without formal formulation and program features. So what we have done so far hopefully convince you even to think about this problem and zoom into relevant applications. We see a lot of conceptual challenges, and I promise you there's more to come. Our contribution, which is embodied by classical differentiable programming language, is a formal formulation of the quantum version of it. In particular, we need to model the parameterized quantum programs and model the semantics of differentiation in quantum programming language, design code transformation, and support other features. Moreover, we implement a prototype of our language design that enable us to achieve the first quantum Neuro-Symbolic application and also run resource analysis both analytically and empirically. Let's look into some basic formulation. We use a parameterized quantum wall language to model version of quantum circuits. In particular, we use classically parameterized polyrotation gates for the parameterized unitaries. This is because they form a universal gate set and can be readily implemented on near-term quantum machine. We also directly model quantum observables by observable semantics, which has three key parameters. One is the observable itself, the other is the input, and the third is the quantum circuit. And it matches the exact formula we have seen before. Note that this observable semantics serve two purposes. One is going to be the target to differentiate about infinite loss function. Second, it also models the output of any quantum program. This is useful to make sense of, saying, one program computing the derivative of the other one. Note that the one program we have going to be the partial p partial theta. Its observable semantics going to compute the actual partial observable semantics of the original p over partial theta. Moreover, note that in this definition, we have freedom choosing the quantifier over OY and rho x. In fact, we have the actual combination. However, it turns out we can have the strongest combination. In particular, this means we only have one partial p partial theta that's going to work for any pair of OY and rho x. This is a very strong requirement that we show it's achievable, also critical for showing our properties. With this setup, we move to consider code transformation. Still consider a very basic case that p theta will be u1 theta and u2 theta. You need to believe me that according to the calculation based on quantum mechanics, this actually corresponds to the case of a classical modification, as we've seen before. And even symbolically, it will match something similar. The critical part is that we need to make sense of the plus operator in both quantum and classical case. So classically, the plus operator means we need to run both parts on input and sum their outputs. Quantumly, we hope to do the same thing. However, the input state cannot be cloned. And when you run on top of that, it will be consumed. So that means if we want to run partial p partial theta, you need to run a collection of programs on the copies of initial state, which is a complication for code transformation. Ideally, we hope to have a similar code transformation like classical for intuition and easy implementation. But still, we want to be able to keep track of the right collection of program in an efficient way. Moreover, we hope to control the size of the collection for efficiency. Our solution is a two-stage code transformation scheme. Instead of going directly from parameterized quantum program to the collection of programs, we add an intermediate object called additive programs. Now, all the code transformation and differential semantics is between the parameterized quantum program and additive programs. Only when one wants to recover the particular collection of programs and run them on a quantum machine, one just needs to compile the corresponding additive program for that purpose. Precisely, the way we define additive program is by extending quantum wire programs with exactly the sum operator we have seen before. Its particular operation semantics tells you have either way, choosing either branches. This matches exactly the intuition we're looking for of the sum operator. The compilation part basically wants to output collection of quantum programs while keeping the size small. Take our previous example, partial p partial theta now has actual meaning because we define the sum operation now. It means, in particular, means we have either or choices. If we combine them, it will return exactly those branches and give you size 2 collection for programs. The general compilation follows the same intuition, but just be more complicated. With this two-stage co-transformation, now the original co-transformation only happened between the parameterized quantum program and additive programs. So here's the list of the co-transformation. We actually have a logic to show its correctness. If you stay at those transformations, it's actually very similar to the classical ones. And this is indeed our design purpose. It will only be very convenient for the compiler implementation. However, there's still a few things we want to highlight. The first part is you look into the very basic, we're talking about single or two-qubit quantum operations. So for those basic gadgets, we actually need to modify the existing ones with something called the phase shift rule that using two circuit difference, we only have one circuit with superposed control for the same purpose. And this is important for composition and efficiency. Second, we want to highlight the proof of sequence rule, which relies on the strong requirement we have defined in differential semantics. We need to skip a little bit of steps, but at a very high level, in order to show the sequence rule, say for the S0, S1, we need to establish this equation and want to use the premise of the partial S0 and the partial S1. However, in order to do that, we need to deal with different observable and input. So fortunately, our strong requirement says you can deal with any theory combination. Thirdly, we want to highlight our co-transformation support case unconditionally and also support a bounding loop, which matches what we already have from classical case. You probably have already heard that. Let's just recap what we have covered so far. We start with the formulation of the variational quantum circuits and all the way to the two-stage co-transformation. Now we're going to talk about the implementation and how we make use of our implementation for resource estimation and the quantum Neuro-Symbolic application. Let's start with the resource estimation. So our goal is to make sure the final collection of programs is reasonable. However, this is not generally true for arbitrary additive programs. Fortunately, if we only care about those programs coming from taking the derivative of an actual quantum program, then we can show the number of the final programs in the collection is bounded by the occurrence account of the parameter theta. So we have a formal definition of the occurrence count of theta, but basically it just counts the number of appearances of the theta. For example, let's consider p theta will be u1 theta, u2 theta. You have theta appearing in both u1 and u2, so occurrence count is 2. As we've seen before, its compilation will give you a collection of also size 2. One question here is that why occurrence count could be a reasonable quantity. To see that, we need to think about the classical example, V3 equals V1 times V2. By our definition, V3 actually have occurrence count 2 of theta. So instead of having actual initial state, classically, if you want to compute the V3 dot, you need to have two actual registers to store V1 dot and V2 dot. So in other words, occurrence account refers to the actual resource you use either in the quantum case or in the classical case, just of different form. And we actually do more tests empirically on the benchmark sets and show this resource bound always holds. Finally, we provide one quantum Neuro-Symbolic application. Consider Q gamma as just a collection of parameterized quantum gates. P1 will be just a Q theta and a Q psi, two Q with different parameters. P2, however, has the first part of Q theta, but it does a quantum control for the second part. In particular, it will measure the first qubit and get out the result, then apply potentially different parameters to Q. Note that in a single run, P1 and P2 will run exactly the same number of gates. We use P1 and P2 as parameterized quantum programs for the following simple classification tests with square loss functions. Here's what we get. So the training of the P2 is totally conducted on our implementation, where the training of the P1 is conducted using pure art. Note that the P2 is the one with control and supported in our case, but P1 is the one without. You can see qualitative difference between P1 and P2. So P2 is much better. So this actually tells you the use of quantum control could be very, very significant for near term, given that it has the same number of gates in use. Let's conclude. We provide a formulation of a differentiable program language with many interesting open questions, like for functional ones or more neuro-symbolic apps. Even if you're only interested in classical program language, our findings might provide hints of unifying differentiable or probabilistic programming, as we are generalization of both. Thank you for your attention.